All right, chapter 9, inferences from two samples. All right, so we've learned that we make inferences back to populations based on our measures from a representative sample that we hope is representative. When we use samples, we are looking at a t-distribution. So far, we've compared one sample to a hypothesized mean. But what if we want to do more sophisticated questions and look at potential differences between two groups? We're going to do compare two proportions, two means from independent samples, and then two means from the same sample, dependent samples. And I'm going to skip 9.4. Okay, so comparing proportions. We've already done this when we calculated the sensitivity and specificity. So I'm not going to have you guys do this in the homework because you've already seen how to set up the data, and that's kind of the hardest part. But when we're comparing proportions, we're looking at the probability, or the proportion of 1 is equal to the proportion of group 2, group 1 and group 2, right? So we're just setting them equal in the null hypothesis, and in the alternate hypothesis, we're setting them as not equal. We could rewrite the null hypothesis this way, where the proportion of 1 minus the proportion of 2 is equal to 0, right? Because if they were the same, when you subtract them, you get 0. But I don't like that as much. I just like it's really straightforward just to do it this way. And the book uses p, but I've been taught to use pi because it's in the null hypothesis. We're testing about parameters, so we're just going to keep it like this. The alternate is that they're not equal. And in the book, they're doing right-sided tests, left tail tests, right tail tests. But here we're just going to do the non-directional test going forward because most of the output that is given to us is based on a two-sided test. Okay, so let's think about some possible research questions that this could answer. Is the proportion of males and females who exhibit a certain diagnosis equal? Or is the proportion of errors in two different labs in the same hospital equal? Going forward, all the tests that we have assumptions that have to be met. And if they aren't met, then the findings from our test are suspect. So for this one, we have to know that our samples are from two simple random samples. We have to know that the two samples are independent and not paired. And then for each of the two samples, there are at least 5 successes and at least 5 failures. So that in each cell of the contingency table, you can't have fewer than 5. Okay, so the first example is, do airbags save lives? Example 1 on page 396. I have this X'd out like this because in the book, they have you set it up this way because you have for the hand calculations, but for SPSS, we have to do it like this. So they're testing the claim that the fatality rate of occupants is lower for those with airbags. Our test is going to be that the fatality rate of occupants is different for those with and without airbags. It's just a nuanced difference, but we're not making the claim that one's better than the other, although we know intuitively that it's better to have an airbag than not. So here, we'll assume we have two simple random samples. We know that our populations are independent. You can't be in the dead and the alive group at the same time. And we have at least 5 successes and more than 5 failures. So the null hypothesis states that the proportion of survival equals deaths, right? Here we have it. The book uses the one-sided test, namely that the proportion of those who survived is bigger than those that died. But we're going to use the two-sided alternative hypothesis, which just says that they're not equal. Okay, so we're going to run the SPSS. You set it up just like you would do in the sensitivity specificity examples, where here we had 1 had an airbag, 2 didn't have an airbag, and 1 survived and 2 died. Okay? Then you have to wait to count counts, right? So you click the box, move the count over. Don't forget to do that. Then we go to Analyze, Descriptive Statistics, Crosstabs. Before, we were looking at the cell counts. We were looking at the percentage in the rows and in the columns. But now we want to go here and click on Statistics, and we're going to click this little box for Chi Square, which is the Greek letter X, but we pronounce it Chi. And we're going to ask for this, so now we're going to get a p-value, whereas before we just got percentages. All right, so let's look at the output. Here's where it gets a little bit confusing because the example in the book gives you different numbers, but I just had to calculate it out so you could see how it would work for a one-sided test as opposed to a two-sided test. You can see Our contingency table is fine, right? I don't have any percentages because I didn't ask for them, but these are the totals, just like we had in the first two tables. Our two-sided test is not significant, so p is greater than 0.05. But if we want to match the book, we divide this p-value by 2. So 0.056 divided by 2 is equal to 0.028, which is significant. It just depends on how we phrase our question, our hypotheses, and how we ask our question. And then over here, we get this Pearson Chi Square, which the square root of that is the z-score. They had negative 1.91 because they were looking at a left-sided test, and the way they calculated it and the way they phrase it, it gives you either a negative or a positive, but it doesn't really matter. Right now, what we're going to say is for a two-sided test, it's not significant, but had it been a one-sided test, it would be significant, and we're not going to worry about confidence intervals for this test. And that's basically all I'm going to do with the proportions. I just wanted to see how that worked. All right, so when we conduct an experiment, we want to know if there's a difference between the treatment group and the control group on some outcome measure. There are some assumptions that have to be met in order to do this one. First, that the groups are independent of each other. Second, that the groups have equal variances. This is called homoskedasticity, that they come from two similar groups, not widely different groups. And also that the data roughly follow a normal distribution, which prior to now, you guys have had to do looking at histograms and QQ plots, and it's been a little frustrating because it's hard to see. It's really hard to tell. But now that we know how to deal with p-values, we're going to test this statistically, and I'm going to show you how to do that. So really quick on variables, we have a variable is a quantity or condition that can change. The independent variable is a variable you can manipulate or control. The dependent variable is a variable that you can observe or measure. And a controlled variable is a variable that's kept the same for all conditions. With the independent samples t-test, this test is used when you have two groups and you want to compare them on some continuous outcome variable. Remember our scales of measurement, nominal, ordinal, interval, ratio? In this, our independent variable is nominal or categorical, and that's the IV. And our outcome or dependent variable, the DV, is the interval or ratio, which in SPSS is just calls it scale. Okay, so when I was a student, I sometimes struggled to see how all these things kind of came together. So I'm trying to make this as explicit as possible and to show you the relationship between your research questions and the statistics that you'll use to answer those questions. So last week we did the one group, the one sample t-test, right, where we compared one group average on some measure against a hypothesized average on some measure. And so to come up with a research question that would match that, I would say something like, is the average number of blood donors during the month of March the same as the hypothesized value? And where I would get that hypothesized value would be maybe from the value from last March or the average of the last 5 Marches. And that would be my research question. This week, we're doing independent samples t-test. So these two different groups are different, right? They're independent of each other. We want to know, are they different on this outcome measure? For example, is there a difference in number of blood donors by gender? Because we're only looking at two groups. And I acknowledge that gender is not always binary, but for this example, I'm just going to use it as two groups. All right, so we have an example in the book on page 417. Radiation in baby teeth. Listed below are amounts of strontium-90 in millibecquerels in a simple random sample of baby teeth obtained by Pennsylvania residents and New York residents born after 1979. Conduct an independent sample t-test to determine that the mean amounts of strontium-90 is greater in PA residents than in New York residents. Use alpha is equal to 0.05 and report a confidence interval. So they're saying it's greater in Pennsylvania than New York. So they're saying it's a one-sided test, but we're going to do it as a two-sided test. So the steps that we follow, we state the hypothesis. So the mean of the average number of strontium-90 in Pennsylvania residents is the same as New York. And then the alternate is that they're just not equal. They're not the same. The critical value was set for us. Use alpha is equal to 0.05. We're always going to do that. And then we're going to calculate the test statistic, but we're going to use SPSS. But first, we need to enter our data into SPSS. So the book shows it to us like this, right? We've got Pennsylvania and New York. And you might be tempted to just go Pennsylvania and New York, but that's not how you do it. You have to put all of your outcome measures in one column, and then you have to tell the computer which group that score belonged to. So these ones, I'll show you on the next slide. We have to designate in SPSS a column for each of our variables. Here I have the strontium 90, that's just the levels, right? SPSS won't let you use hyphens, so we use this underscore often. It's the dependent variable, and the column name state is the grouping variable. It's the independent variable. I have to go into variable view and tell SPSS that the ones are Pennsylvania and the twos are New York. And then I just remind you that if you hover over here, that's how you get to the value labels. Okay, so we check our assumptions. The groups are independent of each other. We're going to assume this is true. The groups have equal variances, that they come from two similar groups, that homoscedasticity I was talking about. We're going to look at the Levene's test. In the Levene's test, the null is that there's no difference in variances, so we don't want to reject the null for the Levene's test. Okay, to check normality, you're going to go to Analyze, Descriptive Statistics, come down to Explore, and now we're going to move our dependent variable over here, and our factor over here, our independent variable over here. We're going to collect plots. We're going to uncheck stem and leaf and check normality plots with tests. Now before we would look at our QQ plot and wonder if this one was normal enough, right? But now we know about now that we know about p-values and hypothesis testing, we can test this. We will look at the Shapiro-Wilk test to see if it's normal or not, and it's just like the Levene's test. If it is not significant, then it is normally distributed. And so we're looking at both states and we see they both are not significant. So we have normality because it's not significant. So once we've checked that, we know it's normal. Now we come to Analyze, Compare Means, slide over to Independent Samples t-test. I bring my dependent variable over, and then I bring my grouping variable here, and we get these little question marks. And then here you click Define Groups, and it brings this up. And I could have said 0 and 1, but I said 1 and 2. So I just said Group 1 is 1 and Group 2 is 2. I hit Continue, I hit OK, and it gets us our output. All right, so we get our output. And the first thing we get is our descriptive statistics, and we can see that the Pennsylvania group is larger than that of the New York group, their average strontium levels. And we also see that the standard deviation for Pennsylvania is double that of New York, implying that there's more variability in the Pennsylvania sample. Next, we have to check the assumptions. First, we know that the samples are independent because one comes from Pennsylvania and the other from New York. We check the normality and we know that it's normal. Lastly, we need to check that this variability isn't too large to make true comparisons. So we need to look at the Levene's test, and that's in this first box. Right? We're now using an F distribution instead of the T distribution. We don't have to calculate it, it does it for us. And we have to decide whether we're going to stay in this top row or go into the next row. Equal variance is assumed, equal variance is not assumed. Now here we are significant, which means that they are not the same. And so we have to drop down to this bottom box. So if these two samples have equal variances, we would see that the Levene's test is not significant, meaning the p-value would not be less than 0.05, but here it is. It's significant at 0.017, so we violate this assumption. So we just come to this bottom row, and we are going to use the equal variances not assumed row. Overall, the differences between equal variances assumed and equal variances not assumed are kind of negligible, but it's important for you to understand the differences between the two. And here we see that our test is significant. So now this is our t-value. It's the same for both. It's the degrees of freedom that get adjusted when the variances aren't assumed. And you would just report the, just do one decimal place, 16.0 if you want to round. For the degrees of freedom, you're going to do t is equal to, put the degrees of freedom in the parentheses, and the t is equal to 3.265. It is significant, and then here are our confidence intervals. So if the Levene's test had not been significant, we would use the top row, and it would have still been significant. Okay, hang on, it says we have 24 in our, so we have 12 plus 12, right? But why is our degrees of freedom only 22? You take 1 degree of freedom away from each of the two groups, so the degrees of freedom is n minus 2, so the overall sample size minus 2. You just need this to report your statistics, and if you're using, since we're using the bottom one, you would use that that box. All right, so Cohen's D for 2 independent samples. To do this, you go, you would have to do this pooled standard deviation, which is kind of a pain to use. And so we're just going to go to this effect size calculator. If you click here, it'll take you to this website. You just type in the values and you click calculate and you get the Cohen's D. And that's a pretty large Cohen's D. Okay, so here we would just make our conclusion. We state the conclusion that there is a difference in these 2 sample means, and it's significantly different. We would say that there is a significant difference in the amount of radiation in the baby teeth of Pennsylvania and New York residents, but we're using the lower row here. T of 15.9 is equal to 3.27, P is equal to 0.05, 95% confidence interval 3.9, and 18.4. Cohen's D, which we calculated, is 1.3.